And we're back. Welcome back and happy Thursday. Today, we will continue on with the data plane and pivot to the control plane, take our first look at routing algorithms. But before we begin, some administrative bits. TCP Wireshark Lab is out and it's due the 30th of March, this Tuesday, at 11:59 and 59 seconds p.m. Where we last left off, we talked about network address translation as a way of sharing a single connection publicly facing to the public internet among over 60,000 devices on a home network, and it uses port numbers in order to do that sharing. On the inbound side, this NAT device rewrites the IP address to the private network and based on the port number, and on the outbound side, it rewrites the private address and port number to the public address and a port number. And so NAT is controversial because routers should only interact with layer 3, which is the IP address, but it also rewrites the port number, which is layer 4, the transport layer. All right, let's continue on. So we won't cover IP version 6, but we will look at generalized forwarding in software-defined networking. And so SDN is where networking is going. And so with generalized forwarding, again, for SDN case, we talked about this bifurcation of the aspects of routing into the control plane, which are the global decisions for the path establishment through the routers, and the local decision, which is the forwarding decision, so-called data plane. And instead of a forwarding table in SDN, we have something called a flow table. And that flow table allows you to, in a more sophisticated way, alter the pathways that your packets take through your router switching fabric. That is the set of routers in your ISP. Now, with this flow table, it's called a flow table because you're modifying and defining the flows or the set of routes or paths that your datagrams take, your packets, as they swirl and circulate through the routing infrastructure. And so this flow table consists of a number of fields, a set of header fields that correspond to patterns that are matched, a set of actions that are performed when a pattern, as described by certain pieces of information in the header, are matched to perform these actions, and counters, which will increment and tell you how many matches you had of datagrams to the patterns based on header information. And so we have these flow tables that are calculated by the centralized controller and downloaded into the routers to the control agents that then install these flow tables. And that's when the switching decision happens. That forwarding decision is implemented in the flow table, resulting from that global decision made by the controller. And so a flow is defined by a set of header fields. And a set of header fields implements through the action what's called generalized forwarding, a set of simple packet handling rules. So we have a pattern, and this pattern is used to match values in packet header fields. And I'll describe what those fields are. And they span from the link layer to the network layer headers, as well as to the port number information in the transport layer. And so the set of actions that are available in the action set for matched packets based on these patterns are to drop a packet, to forward a packet out a port number, to modify some value in the packet, or to send a matched packet to the controller, and therefore sampling the traffic that's going across the routing infrastructure. And so you can also have priorities associated with these rules, these entries in the flow table, in order to disambiguate between overlapping patterns. Which one to match? Which one should you enact first? And then counters can count either bytes or packets. And so a flow table in a router is computed and distributed by the controller, and it defines the router's match action rules. What behavior will the router engage in? And this is more generalized router that can implement the behavior of a switch, implement behavior of a traditional router, and implement some of the behaviors associated with a transport layer like a firewall. And so this flow table in a router is distributed by the controller to the control agents running in the routers, and it defines the match action. Okay, so here are some examples. Here we have a source IP address, the 1.2 network, a destination IP address, 3.4.5 network, and the action is to drop that packet. Here we have any source, a wildcard, star.star.star.star, destination, so any packet with a destination on the 3.4 network is going to be forwarded out port 2. That's another match action rule. And then this other one, if the packet is originating at IP address 10.1.2.3, sent to any destination address, send it to the controller. So here we're sampling all of the traffic that's coming out of source 10.1.2.3. That's another match action. And so in the flow table, when we look at the action set, we can forward packets through port numbers, that's one action, encapsulate and forward to the controller, that's sampling. You can drop a packet. You can send through the normal processing pipeline, matching based on the destination IP address, send out a port number, or you can modify fields. That rewriting, it can act like a NAT. And so let's take a look at the set of rules. The set of rules span the link layer, including the MAC address, which we'll learn a little bit later, virtual LAN and Ethernet type, network layer, the source and destination IP address, and the upper layer protocol to which this datagram is delivered, as well as the source port, destination port in the transport layer. And so as such, between the match rules and the action set, you can implement NAT behavior, link layer switch behavior, routing behavior, sampling statistics behavior, as well as firewall behavior on the same device programmatically. And so that's the beauty of this flow table entries and the protocol and system for implementing different flows is called OpenFlow. And it's a well-defined standard that's very popular, growing in popularity. In addition, you also have statistics that can be reported, and these are counts for all of the packets that match a particular rule. So you can look at proportions of traffic or all sorts of things about the flows of data circulating across your routing infrastructure on a router-by-router basis. Quite powerful. And so here are some examples of match action rules. In this case, we have a destination IP address, and we have port 6, and it says IP datagrams, any datagrams that are destined to go to host interface on the network 51.6.0.8, they're going to be forwarded out port 6. So whatever router has this match action rule is going to say, if you're trying to send to that IP address, then get forwarded from the input port on which it arrives out to output port number 6. Now, the firewall behavior, you might have the following. It says, do not forward or block all datagrams that are going to port 22 in TCP. And so here we have destination port 22, and the action is going to be the drop action. So it's acting like a firewall. Here's another one. Do not forward or block all datagrams sent by a particular host. So if the source IP address is 128.119.1.1, drop the packet. So this router blacklists that particular host. I won't allow you to send data off the network. And so all sorts of behaviors we can have. Let's take a look at switch-like behavior. If you have a MAC address on a network for a particular host, and we'll talk about MAC addresses when we get to the link layer module, but this MAC address uniquely defines a particular network card on a single network, on a subnet. And so what this match action rule does, it says if frames from a particular MAC address are originated, they're going to be forwarded out port 6. So this acts like a switch. It ushers along these datagrams through a port based on the MAC address. All right. So the match action rule can unify different types of devices. You can have the same device programmatically act like a NAT, act like a switch and link layer, act like a router, or act like a firewall, impacting all of the ways you can shape the traffic that goes across your network. And so when you act like a router through a match action rule, you're matching the longest destination IP address prefix, and the action is to forward out a link. That's exactly what a router does. Acting like a switch, you're looking at the destination MAC address, and you're going to forward out a port, or you're going to flood. You're going to send out all of the ports. That acts like a switch, and I'm going to talk in detail about what switches do. When it acts like a firewall, match action rule, the same device, your router, is going to match the IP address and the port number, and it's either going to permit or deny that traffic. It's acting like a firewall. So all of this flow behavior, the pathway or the shape the data takes through the network, is done on the same device, but it can act differently like a router, switch, or firewall just by having different match action rules for their respective flow tables. And so it acts like a NAT. When you match an IP address and a port number, an action is to rewrite your address and port number as you send out an port or output port on your device. And so here's an example. And in this example, we have datagrams originating at host H6 and H5. They're attached to router S3. And we have host H3 and H4 attached to router S2. And so in this case, we want to shape the data. We want to cause the packets originated at host H6 and H5 to take a path, a specific path through the network. And we can do that with our match action rules through OpenFlow. And we want that pathway to come down here to router S1 and then across here to router S2. So how are we going to do this? So we start out with a match action rule that says if your source IP address is on the 10.3 network and your destination IP address is the 10.2 network, the router S3 is going to forward out port number 3. That implements this edge going down from S3 to S1. Likewise, in router S1, our match action rule is going to say if you have an ingress port, and an ingress port is the port number in which the data arrives, and egress port is the port number out of which data leaves. So if your ingress port number is port number 1, that's this port number that S1 shares with S3, and your source IP address is the 10.3 subnet, your destination IP address is 10.2 subnet, then forward out port 4, that's your egress port number. That's this edge. And so now that means between the match action rule in S3 and router S1, you're going to get the following flow going down along this edge, forwarded out port 4, arriving at router S2. And so now the match action rule for router S2 says if your ingress port is port number 2, that's here, and your destination IP address is 10.2.0.3, it's going to forward out port 3. That's down to this host H3. And likewise, if your destination IP address is 10.2.0.4, it's going to forward out port number 4. That's this edge out to host H4. And so in this case, with these match action rules for router S3, S1, and S2, you can get a very specific shape to your data, forcing the traffic to take a particular route or flow across your route infrastructure over your network. And all of this is set by installing flow tables to each of the routers from your centralized OpenFlow controller. Okay. And so this ends chapter 4, the control plane. Let's switch the data plane. Let's switch to chapter 5 material, which is the control plane. So I'll meet you in the Chapter 5 slide deck. So we're here in Chapter 5, and we're now going to examine the control plane. And that is the set of global decisions and considerations that establishes the pathways through your routing infrastructure. And the result of the control plane is a new set of forwarding tables that are installed in all the routers. Now in SDN, there's an equivalent. The controller forwards a new flow table to each one of the routers. So let's take a look at the routing function. And remember, you have two layer functions for the network layer. There's the forwarding, the moving of packets from the input ports in a router to the appropriate output port, and that was called the data plane. It's the local forwarding decision. And then we have routing, which is the establishment or determination of the route taken by packets end-to-end from the source of the datagram to the destination. And that decision about the end-to-end route means that we have to decide which ports for a router we're going to take along the way between the source and the destination endpoint. And so that decision is made by the control plane. And so there are two approaches you can have for structuring your control plane. One is a logically centralized control, and that's using SDN, and the other is on a router-by-router basis. That's traditional, and that uses a routing algorithm at each router, and they exchange data with other routers that are neighbors in the network. And so per router control plane, you have individual routing algorithms, which are just processes that run on the router processes in each router, and they interact with one another in the control plane, exchanging data about local traffic conditions on the links, and they arrive upon the optimal route across all of the links. So here we have our routers, and we have our local forwarding tables that define the headers and the port numbers, the output port associated with a range or block of IP addresses or subnets. And then we have the routing algorithms that run on the router processors, and they exchange information with one another. Now, as they exchange information with one another, they get a picture of the traffic state across the entire network, and then they use this information to calculate the best path to take and reflect that best path on a router-by-router basis with a setting or an entry in the local forwarding table. And so here, once the routing algorithm converges, it downloads a new forwarding table, installs that into the router to impact the new forwarding decision that implements those end-to-end routes that were calculated by the routing algorithms. And so we have our control plane and our data plane. And with a logically centralized approach in software-defined networking, we replace the routing algorithms with control agents, and the control agents effectively are these very simple proxies, but all of the real computation and the smarts, so to speak, happen in the remote controller. And so the controller interacts with the control agent to download a new forwarding table, and the control agent sends up information about traffic and data to the controller as the basis that it uses for its decision or calculation. And so here we have the controller. Once it establishes the end-to-end routes, it downloads the new forwarding table, sends them to the control agents, and the control agents install them in the routers to implement the new match-action rules for the forwarding or the other match-action behaviors that you'd have in a software-defined networking scenario to impact the flows for datagrams going across our routing infrastructure. And so here we have the control plane, which is that global end-to-end path decision-making, and the data plane, which is effectively the match-action rules that impact the forwarding decision or the match-action behaviors in the individual routers. And so let's take a look at the routing protocols, the establishment of these routes. And the routing protocol is the determination of good paths or routes from a sender to receiver through a network of routers. So you're going across one hop to one router, another hop to another router, traversing link after link after link, being stored and forwarded, stored and forwarded, stored and forwarded across to the destination. And so a path is going to be represented as a sequence of routers that your packets traverse from a source to a destination host. And so a so-called good route is one that's either the fastest or more generally has the least cost, and cost can be determined in a number of different fashions. It could be the least congested. It could be the most lightly loaded. It could be the smallest number of hops. There are many ways to quantify this idea of a good route. And so routing is one of those major deals, a top 10 issue in networking. And so let's take a look at a graph abstraction of the network. And a graph is an ordered pair, set of edges E, a set of nodes N. The N nodes are our routers. And in this case, we have a node set UV, W, X, Y, Z. And we have a set of links or edges, and these are the individual paths between router pairs. And so in this case, our edges are bidirectional. So edge UV is the same as edge VU. So we only depict it once. And so we use a graph abstraction to represent our network because we have sophisticated tools, specifically Dijkstra's algorithm, that we can use to determine the best or least cost path between a source and all other nodes or routers, all other destinations. Now, effectively, when we talk about a router, what we really talk about is a subnet that's managed by that particular router. But we're going to depict these routers as nodes and give them these alphabetic characters because we're going to abstract it as a graph. Okay, so the cost of a link we're going to call C, and C of x prime from one node to the next and one router to the next is going to have a number, and we decorate our edges with the cost associated with that link. Now, of course, the cost could be determined by a whole host of things. It could be the physical cost, like it's cheaper to send over copper wire than via satellite, or it could be congestion. There are all sorts of ways you can physically map cost. And so if a cost is 1 for every link, then the least cost path is going to be the one that's the smallest number of links or hops you traverse from the source to the destination endpoint. And so if we have a path consisting of a set of nodes in the network, and let's say there are P many nodes going from node 1 to node 2 to node 3, etc., up to including node P, that's just the path cost of the individual links from node 1 to node 2, then 2 to 3, 3 to 4, P minus 1, and ultimately to P. And so a key question is, what is the least cost path between U and Z? How do we determine this? And it's the routing algorithm's job, run by this process that's in each router, to find or determine what this least cost path is. And so there are different flavors, as it were, of routing algorithm. One is global, meaning all routers have complete information about the so-called link cost or link state. These are called link state algorithms. And they use in the literature the name topology because you're really looking at the relative relationship between pairs of nodes, almost like a type of geometric measurement. This cost you could think of almost like as a weird kind of distance, and it is. How much units of work do you do in order to get from one node to another? And so link state routing algorithms are global in their view because each router, as a prerequisite of link state routing algorithms, has all of the path or link cost information. Then there's another one that's decentralized, so-called distance vector routing algorithms. And these distance vector routing algorithms are decentralized. Each router's routing algorithm exchanges local information about the links they are connected to with their neighbors. And of course, if neighbors are connected to other neighbors, eventually all of this local link cost information washes across the network. And so there's an iterative process in these distance vector routing algorithms where neighbors exchange, or routers that share a link, exchange link information. And so you tell your neighbor, and your neighbor tells its neighbor, and its neighbor tells its neighbor. And so these distance vector routing algorithms eventually converge to having an understanding, rather, of the path cost across the network. And so another way of describing your routing algorithms is whether they're static or dynamic. Now, static routes change very slowly over time. The path cost or the link cost don't change very much. Dynamic routes, these link costs change more quickly. So that means you're going to have continual updates after some periods of time, again and again and again, and the overall path costs are then going to change to reflect the changes to these individual link costs. And so we have these four ways of categorizing our routing algorithms. So let's take a look at link state routing. Now, the key algorithm here is Dijkstra's algorithm, and it makes the assumption that the link state is known to all the nodes. So that means before the algorithm runs, that each router engages in something called a link state broadcast, so that all of the routers have all of the link information of all the other routers. So once Dijkstra's algorithm completes this broadcast and all the routers are complete in this global information about all the link costs for the topology of the network, Dijkstra's algorithm runs and computes the least cost path from one node, the source node, to all other nodes. And so once this Dijkstra's algorithm completes, it then gives the forwarding table for that particular node associated with the running of Dijkstra's algorithm. And so what it does is iteratively, after some number of rounds, one by one, it adds the closest nodes on the network to the least cost path, because the least cost end-to-end path includes individual hops that are themselves the smallest cost. And so in our notation, we're going to have CXY is going to be the link cost from node X to node Y. And if you, in the beginning, are not direct neighbors, it's going to be set to infinity. Then we also have this D of V. Now, D of V is the current value, so it's going to be updated, of the cost of a path from the source node in which Dijkstra's algorithm runs to some destination B. And that D of V is often called a distance vector. It's the cost of the distance from a source node to router or node V. And then P of V is going to be the predecessor node. It's the node by name that is along the path from the source to node V. So this predecessor is going to show you which way do you go to get back to the source from some node V. Okay. So then we also have N prime. N prime is going to be this dynamic thing, like a blob, if you will. And N prime is going to be the set of nodes whose least cost path is absolutely known. And one at a time, we're going to add another node and another node and another node to this N prime, and it's going to be grown until it encompasses all of the nodes in this particular network. All right. So this is Dijkstra's algorithm. We're going to start out with the source node U, and that's going to be our convention. And then for each of the nodes that we have in our network, we'll call them V, you're going to see if V is adjacent, if it's a direct neighbor to you, then we're going to fill in the distance vector, the distance to get from U to V. If it's not a direct neighbor, we're going to start out with that distance vector to be infinity, and then we're going to improve on it. So we start out in our loop after we do this initialization, and we're going to say, okay, well, let's look at all the nodes that currently are not on the least cost path N prime. We start out with the least cost path for U is going to be that source U. It's the least cost path without this path cost is 0. So that makes sense to start with N prime as U. So now you're going to say find some node, call it W, not in N prime, so that its distance vector is minimal. What's the closest current node? And you're going to add that node to N prime. I call it growing the blob. Now once you add it to N prime, now you're going to see, okay, if I know W is closest to what's already in N prime, can I improve upon the distance vector from V by going indirectly through W? If W is closer, okay, well maybe my distance vector to get to V can be improved by either keeping V, that means it's the best least cost, or going to W and then making that single hop to V. And so essentially, I have my node U, and I have my node V. And I'm asking the question, is it better to take whatever my path cost is to get to V, or is it better to go to W from U and then take that single hop from W to Z? And that's what I'm asking when I run this minimization. Can I improve upon the least cost path to V by going indirectly from W to V by going from U to W? Okay. And so I keep doing that again and again and again until eventually I run out of nodes, and then I stop, and all of my predecessors, if I update my least cost path, instead of going from U to V, going through W, my predecessor in the beginning is going to be this way from V. I'm going to update it to go through W if I think that's a better least cost path. All right, so let's take a look at an example. And here I have nodes U, W, X, V, Y, and Z. So I'm going to start out running Dijkstra's algorithm in node U. That's going to be my source. And I'm going to set N prime to U. So this N prime starts out as U. Now, of course, in my initialization, I look at all the neighbors of U. That's my neighbor is X, W, and V. So I set my distance vector for VWX to 7, because that's 7 going from that neighbor from U to V. That's 3 going from W to U. And that's 5 going from X to U. Now, the predecessor for the V node, that predecessor is U, because V goes directly to U in order to get to U. W, that predecessor is U, and X, that predecessor is also U. Everything else, that Y and Z, their distance vector is going to be infinity because they're not directly connected neighbors to node U. So now I'm going to say, okay, which is the node that's closest to U in my N prime? That's going to be W, because W has a distance vector of 3. So I then add my W to N prime. That's where I grow the blob. So now my N prime is going to include W. And so now I ask the question, let me look at all of the neighbors of W, and W's neighbors are X, V, and Y. And I ask myself, do I keep the same path from U to X, V, and Y, or do I go from U to W and then go from W to X, V, and Y? Which is a better path? So if I look at W's neighbors, well, U was already in the blob and prime, so I don't consider U. X, if I look at X, well, if I go through W from X to get to U, that's a cost of 4 plus 3 is 7. Whereas before, to get to X, that was a cost of 5. That's a cheaper cost, so I'm not going to do that update. I'm going to keep that direct link, that predecessor, to get from X to W. If I look to go from W to V, well, from W to V, that's 3 to get to W, 3 to get to U, that's 6. That's actually cheaper than the 7. So I'm going to make that update, and if I want to go from U to V, I'm going to go indirectly through W at a cost of 6 total to get to V. So my predecessor for V, that cost is going to change to 6, and my predecessor is going to change to be W. And then lastly, if I want to get from U to Y, well, that was infinity. So absolutely, it's cheaper than infinity to go 8 plus 3 at a cost of 11, and the predecessor for Y is going to be a cost of 11. Predecessors is going to be W. So let's now look at that change. So here we have 6W, and our predecessor from V is W, and the cost is 6. And then we have 5U, right, for X. That hasn't changed. And we have 11W for node Y. Okay, so now that we've grown that blob, we're going to take the next closest node to what's in to U. And so now when we look at that, we see that 5 is the smallest distance vector. So we're going to add node x to the blob. So if we add node x to the blob, well, what do? This blob grows, and now node x is now added to the blob. So for node x, we look at node x's neighbors. Well, its neighbors are w, u, y, and z. Well, w and u are already in the least cost path. The blob already consumed. So what's left is y and z. So if we consider y, well, the distance vector to y was 11 going through w. That's this path. And if we go indirectly through x, we said 11. That is y, cost of 7 to x, cost of 5 to u. 7 plus 5 is 12. That's greater than 11. So it's much better to keep the old path. So we're not going to make that update. We're going to continue with the 11w. So let's look at z. Z had an infinite distance vector to get to u. And so, yeah, that's better. So we're going to go indirectly from z to x. So that's a cost of 9 plus a cost of 5. 9 plus 5 is 14. So that's going to be 14 at a cost. The predecessor for z is going to be x. Okay, so let's do that update. So there's our 14x for node z. So now we're going to look at our distance vectors, and we notice v is the next closest node. So we're going to add v to our least cost path. And so this blob is going to grow one more time, and we're going to now consume v. These neighbors are u, w, and y, and u and w are already in the least cost path and prime. And so we're only going to consider v's neighbor y. So y is at a distance of 11 to get to u, and that goes through node w and to u at a cost of 8 plus 3, that's 11. And so we want to consider going indirectly through v. So if we go indirectly through v, well, to get from y to v, that's 4. And then v went through w. 4 plus 3 is 7, plus another 3, that's 10. So that's going to be 10 if we go from y to v, and then from v to w to u. And that's actually cheaper than the current distance vector 11. So we're going to actually change the route from y, its predecessor, instead of w. It's going to be a cost of 10, and its predecessor is going to change to v. Okay, so let's fill that in. So now we're going to take the next closest node by its distance vector. That's node y. So we add y to the least cost path list. So there's y. The blob grows one more time. And y has neighbors v, w, and x, and z. Now v, w, and x are already in the least cost path. The only other consideration is node z. Node z currently has a path cost of 14 to get to u. It goes through its predecessor x, 9, plus 5 more to get to u, that's 14. Now if we go indirectly through y, z would go to y, that's 2. 2 plus y going to v, that's 4. 6 plus 3 is 9, plus 3 is 12. So that is actually cheaper. It would be at a cost of 12 going indirectly through y, 12y. So now we write that 12y, and then we add the next closest node, which is z, growing the blob, and z doesn't have any neighbors that are not already in the least cost path. And so now this is our result. And if we look at all these predecessors, we construct the shortest path tree by tracing all these predecessors. So we have z's predecessor y, y's predecessor v, v's predecessor w, w's predecessor u, x's predecessor u. And this is going to be our least cost path tree. We're going to have u going to x, u going to w, we're going to have w going to v, we're going to have v going to y, and we're going to have y going to z. And using this set of edges, we construct the least cost path. There's 5, that's 3, that's 3, that's 4, and that's 2. And so now we can get from node U to any other node in the network, any other router, over this path is fully connected. And moreover, once we set the forwarding table, we're saying if your traffic is destined for subnet managed by router X, we're going to go through this port number instead of that port. So we have complete information for the forwarding table for node U in order to get to every subnet managed by each router. To go to subnet managed by W, you go through this port. To go to subnet managed by V, you go through this port. By Y, you go through that port. By Z, you go through that port. And we set our forwarding table accordingly. Okay. So let's look at this other example. It's another example, and we're going to go through a little bit faster. We start out in node U. We have U, V, X, W, Y, Z. And we start out with our initialization in step 1. We have all of the direct neighbors. Use direct neighbors are W, V, and X. So we have V, cost of 2, W, cost of 5. We have X, cost of 1, and for Y and Z, it's infinity. Y and Z is infinity because they're not directly connected neighbors. So now, if we look at this, X is closest, so we're going to add X. So we add X. Now the blob grows like this. So if we look at X's neighbors are V, U, W, and Y. So we consider V, W, and Y. So if we're at X and we go to V, well, V was already at a cost of 2. So if we go from V to X, that's 2 plus 1 is 3, so it's better to keep the old path for V. So we don't touch V. So we don't leave that, we leave that alone. So that's going to stay put. So now W's cost was 5, but if we go from W to X, that's 3 plus 1 is 4. It actually improves. So we're going to go in through X, and we're going to set the predecessor from W to X, and it's going to be a path cost of 4. So we're going to change that. And so then Y had an infinite cost. Anything's better than infinity. So we go from Y to X, X to U, cost of 2, and the predecessor for Y is going to be X. So now then, we look at the next closest by distance vector. X has already been added, and we have a tie here. So we're just going to break the tie and just going to choose Y. And we add Y, okay. If we add Y, we grow the blob. And now we look at Y's neighbors. X, well, it's already in the least cost path, so we're going to look at W, and we're going to look at Z. So if we add Y and we look at W, W had a cost of 4. W's cost was going through to X and then U at a cost of 4. But if we go from W to Y, that's 1, 2, 3. It goes down to 3. So we're going to change W. Its predecessor is going to be going through Y, and its cost to get to U is going to be 3. Okay, so that's going to be updated. So that's W. Let's look at Z. So if we look at Z, well, Z was infinity. Anything's better than infinity. So if we go from Z to Y, that's 2. Y to X, X to U, that's 4. So it's going to be cost of 4 from Z, and we're going to use predecessor path to Y from Z in order to get to U. So now, for this line, we're going to look for the next smallest one. That's going to be V. So now we're going to add V to the blob. And so if we add V to the blob, this blob grows up, and it consumes V. So now we look at V's neighbors. These neighbors are U, X, and W. Well, U and X are already in the least cost path. So when we add this V, we're going to only look at W. So if we look at W, well, W already had a path cost of 3 going through Y. And so W went down to Y, that's 1, to X, that's 1, to U, that's 2, then 3. So if we go from W to V, that's going to be 3, and then from V to U is 2, that's 5. Well, it's better to keep W's existing path going to predecessor Y, so we're going to keep that 3Y. Okay, so now we don't have any more neighbors for V that aren't already in the least cost path. So now we're going to look at which one is cheaper. Well, that's going to be W. So we're going to add W to the blob. So we add W to the blob grows this way, And W's neighbors are U, V, X, and Y, and Z. Well, U, V, X, and Y are already in the least cost path. The only neighbor left that's not in the least cost path is Z. So then we ask the question, do we keep our path cost for Z, which is 4, predecessor going through Y along the bottom edge here, 2 plus 1 is 3, plus 1 is 4, or do we go through W? If we go through W, that's a cost of 5, plus 1 is 6, plus 1 is 7, plus 1 is 8. That's 8. It's better to keep the old path going through Y, along the bottom from Z to Y to X, and then to U. So we keep that, and now we add the closest node, that's the one remaining Z. Z does not have any neighbors that aren't already in the least cost path, and this is our result. And so we have our predecessor Y, our predecessor here for X. Let me draw a double circle around it. That's Y, that's X. Predecessor for X going to U, predecessor for W going to Y, predecessor for V going through U. And so if we take these predecessors and assemble them together, now this is our least cost path tree from U to get to V, to X, along this port or output port, to get to W, to get to Y, or to get to Z. So now in node U, in the forwarding table, we say if our destination is address managed by router V, or subnets managed by router V, we would use the link UV. If it's subnet managed by X, we use the link UX. If it's a subnet managed by Y, we use UX. If it's managed by W, we use UX. If it's managed by Z, we use UX. And this is going to be the forwarding table that we install into router U. Okay, and so these are two different examples of link state routing using Dijkstra's algorithm to arrive upon the least cost path by assembling the predecessors to represent the least cost path tree, and then we set the forwarding table in that source node once Dijkstra's algorithm has converged. It's exhausted all of the nodes in the network, adding them one by one based on their closest distance vector, one at a time, and then fixing up the intermediate path, arriving upon the least cost path tree. All right, so with that, I'll end there. And as usual, please stay healthy, stay safe, and I'll see you all on Tuesday.